For 3B, in 3A we just created the model, we didn't actually run it. In 3B we are going to use these initial conditions and this particular input to run our model from time 0 through 5. So we go to the model, we make sure the running time is set to 5, and we have a block that we got from the sources page, a sine wave, and we have configured it to be a sine wave with an amplitude of 1.2, no DC shift, and a frequency of 0.75 radians per second. The sample time thing is, we shouldn't really be concerned about this because it will be determined by the system. Just leave it at 0. And the initial conditions given in the problem, we are given an initial condition for the position x and the velocity x dot. So this is our variable x coming out of this second integrator. So the initial condition for x will be put in here, the initial condition of 0.4, and the initial condition for x dot, because it's coming out of this integrator, you would put that in here. Then you can run this thing. You hear that ding sound, that's when it finishes running it for 5 seconds. And these are the plots. So I have a scope labeled input, and this is the sine wave that we were feeding to the system, and the scope at the output. And when we are looking at these plots, it's a good idea to hit these binoculars. It automatically scales your plot to get you the details. It zooms it to the right size. So this is the response to this input. And is our result same as the result from problem 2? It's not, because if you compare, it's kind of the same when we are looking ahead in time, but initially this curve starts at time at a position of 0.4, and this starts at 0, because in problem 2 we weren't given any initial conditions. We started with 0 initial conditions. In this problem we have a different set of initial conditions, so our plots do not look the same. In part C, we are supposed to replace this source or use a source of a particular frequency, get the output, then change the frequency and amplitude to something else, get the new output, and then eventually for the third time replace the input as the sum of the two inputs that you've used before, and then look at the output. The output should be the sum of the two outputs you saw earlier. You can either do that, or you can just have two sine wave generators with different amplitudes and frequencies. So this has this amplitude, this frequency. This guy has this amplitude and this frequency. They are put through a summer. I can use a switch to manually turn them on or off. So right now the system is only being fed this sine wave, and the output corresponds to f of 1. Now the system is only being fed this sine wave, and I'm getting an output corresponding to this source. Then I'm going to turn them both on. They'll get added together, and the output that you get should look like the sum of the previous two outputs. And in this case, they've asked you to use 0 initial conditions, so make sure you make that change. You get into the integrators and get rid of these initial conditions. And then you can just include all three plots, and it should be apparent that this is satisfied. This property is called linearity or superposition. In this part, you were supposed to design a custom source that produces a pulse, and then a custom source that produces this kind of a signal using only steps and ramps. And if you have some knowledge of simulating, it should not be that hard. But to produce this particular step, you will have one step that turns on at time 1 and has an amplitude of 10, something like this. So I have a step that turns on at time 1 initially, which is 0, and eventually settles at 10. And then at time 2.5, I want to bring it back to 0. So I can subtract another step that starts at time 2.5 and has an amplitude of 10. So here's my second step, which starts at time 2.5 and has an amplitude of, I've used minus 10 because I'll just add them together. So that brings it back down to 0. And if you run this and hit the binoculars, you get that thing. A pulse from 1 through 2.5. I should run it a little longer. So there's that pulse. For the second case, you have a ramp starting at time 1. So this ramp has a slope. We need to calculate the slope of this ramp. So it will be the y divided by the x. Y is 1.2, the x is 0.1. So the slope should be 12. So, so I have a ramp that starts at time 1 and the slope of 12 initially, which is based at 0. So this will produce a ramp that keeps going up like that. At time 1.1, I want to bring it back to a flat curve. So I'm going to subtract the same ramp. A ramp starting at this time, when subtracted from this ramp, would yield a flat curve. So I have a ramp with a negative 12 slope starting at time 1.1, and when it's added into it, it makes it flat. At time 1.3, you want a negative going slope, so you and the negative going slope, the magnitude of the slope is y over x. The y is 0.2 and the x is 0.1. So it should have a slope of negative 2. So here there's a slope of negative 2 starting at time 1.3. When that kind of a ramp starting at time 1.3 and going in this direction is subtracted from a flat curve, you get something like this, which is continuing to head downwards. And at time 1.4, we want to bring it back to a level output. So we add a ramp of slope plus 2 starting at time 1.4. And here it is. We can just zoom into this portion. So this works. And for the last part, you were just asked to copy over these blocks into your into, for example, this Simulink model, and get rid of this sine wave and paste your those blocks in here and use those as the input instead of the sine wave. So that's everything for this lab. And if anything was not clear in this video, you can just send the GTAs an email or just see them during their office hours. Thanks.